Okay, we're continuing our discussion of regression, but this time we're talking about logistic regression.
This is an example of classification. Instead of predicting a real number, we're going to predict probabilities of a set of outcomes. You can use classification for deciding whether to stick an ad next to a search result or to detect whether an email is spam or not.
These are text applications, but you can also use classification in other settings. So like determining whether or not a photo has a bird in it.
This is a very common building block of machine learning methods, and stochastic gradient descent for logistic regression will be a very useful example for what we'll do in more complicated methods.
So logistic regression has a fairly simple definition. Here it is. Like linear regression, we have some weight vector and some observations. We'll just focus on binary classification. Here it's based on this formula. Today we'll just assume that one class is 0 and the other class is 1. Let's do a sanity check. What happens if all of the betas are 0?
Okay, if all of the betas are 0, then the argument to the x function will be 0 because you're multiplying x's, and no matter what they are, you'll be multiplying them by 0, so the answer is still 0. So the probability of y equals 0 is 1 over 1 plus 1, or 1/2. For y equals 1, it would be 1 over 1 plus 1, again, 1/2.
Right, so if your betas are 0, you don't know anything. You just assume that all classes are equally likely.
This looks a lot like linear regression that we just talked about, except for the x and the sigma here. What's that?
The Greek letter sigma stands for the logistic function. Let's refresh your memory if you haven't seen that before.
Okay, so the x function is e to the x, where e is a magic number around 2.7, and the sigmoid function squashes numbers into the range between 0 and 1.
And that's why it's so important. The dot product of beta and x passed through the logistic function gives the probability of y equals 0, and 1 minus that gives the probability of y equals 1.
If the dot product is really negative, then that means that y equals 0 has a much higher probability, a probability closer to 1. And if the dot product is really positive, that means y equals 1 instead has a much higher probability.
Right. The other nice thing about this is that it has a very simple derivative.
So the only real difference between this and normal regression is that we turn the outputs into probabilities.
We want to have outputs that lie in the range from 0 to 1. The logistic function is a convenient way to make that happen. And it does so in a way that's nice because you don't have to constrain its inputs. It's nicely differentiable, and it gives you a probability. Let's see an example for spam classification. Here are some weights for features. Let's classify an empty document.
Okay, is this just both classes get 0.5 probability like we did before?
Nope, because we have the bias term. Remember, which always contributes even if there are no real features.
Okay, then the input to the logistic function is 0.1. That's always there, even if there's no other features in the input. This is called the bias term. We have 0.48 probability of y equals 0, not spam, and 0.52 for spam.
Good, and if you had to say one class or another, you'd give the higher probability spam. Let's try a more complicated example with 2 words.
Okay, so we add the bias term again, as always, to that of mother, which is -1. We now have a total of negative 0.9 to Nigeria, which gives us a total of 2.1. After passing it through the logistic function, it gives a probability of spam being 0.88.
Right, here's one last example. If you have multiple instances of a feature, you multiply the number of times a feature is present by the feature weight.
Is the feature vector x always the count of the number of words in a document if we're using text data?
No, we'll talk more about how to set up feature vectors later. This could be anything from TF-IDF vectors to transformations of the vectors.
For linear regression, we had a closed form solution for finding the model weights beta, and you hinted that that wouldn't be the case here.
That's right. And next, we'll use a loss function for logistic regression to learn the weights of a model from data in the next video.
If you want to see more videos like this, check the video description for the course that comes from the link down below. You can then see the context and the correct order for watching these videos. YouTube will gleefully show you stuff in the wrong order. If you want other people to see this video, provide a big gradient to the recommendation algorithm by clicking the like and subscribe button down below.